Hey, thanks for joining me. Today what I want to talk about is the structure of materials, how everything fits together, what everything looks like if you look close enough is basically the theme. So here's the big idea, is if you really look at things closely, nothing is really simple. If you look at a piece of chalk, it's really an aggregate of little white things, often little old sea creatures from millions of years ago, little pieces of dust or dirt, rock from a long time ago. Your fingernail is collagen that has a very complicated structure. Things come together in a sort of three-dimensional web-like structure. If you look at your car tire, it might seem like a simple piece of rubber, but really inside that there's other things like carbon black particles, there's Kevlar roving in there, there's steel belts, all kinds of things going there if you look at the structure closely. Even if you look at something like a steel nail, I'll show you some examples from carbon steel in a little while. There's a whole lot going on. There's crystals, there's defects in those crystals, there's multiple different types of crystals sticking together. Those things all come together and fill shape, fill space in some kind of a complicated way. So point is, all real materials have complex structures, and there are features there and there are defects on multiple length scales. It's really those structures and those defects that really lead to the properties that we rely on as engineers. And what we do in material science is we really try to engineer those structures to give us the things that we want. So to make it simple, I'm going to get to making it simple later. First, let me tell you what we want to do with this short lecture. First, talk about what we mean when we say microstructure, talk about the key features, show you a couple key microstructures, a couple simple ones. This is the kind of stuff that material scientists really live for, is what does a microstructure look like. We're going to focus on the sizes because that's a nice quantitative thing we can get at. If you can understand the size scales, you can understand a lot. We're going to introduce the word phase, which is a key word in material science. We're also going to think about how we can interrogate or how we can measure what structure looks like. Could be the key methods that we use for that. So first, let's start really big to kind of set your expectations, show what we're looking for. If you're getting a nice new kitchen, nice countertop, we had our kitchen done a little while ago. I got to go to a store where they did granite. Back in places like Italy and Brazil, there are big mines like this. So they cut out big cubes of granite. These things are 10 feet or so each dimension. Cut them up, and then they slice these things more or less like bologna. They polish the surfaces, and they end up with these granite slabs, and there are some places that have just hundreds of these things on display. You can go look at them. And to me, these things look just like microstructures. And you're going to have to excuse me for just 1 second here. Excuse me, I had another movie going that I had to turn off, or long story. So anyway, here's an example of granite. You can imagine what happened here. And this is the other thing. Microstructure tells a story. This is a metamorphic rock. It was probably laid down in layers like this. And then under the heat and pressure of the earth, it turned into granite. But you can see various layers in there. You can see other things here. These look like they're chemically different than what's here just by eye. You can see different sorts of features in them. If you look closely, you can see some other little crystalline features. This is what I mean by structure. This is a macrostructure, and this is macro because we say this is about 8 feet long, whereas normally we're going to put scale markers on here that are much, much shorter than that. The point is you can see different features, you can see different chemistry, and if you're good at it, you can really engineer these sorts of things. Here's an example of, again, granite telling a story. There's fossils in here. Again, this is about a 10-foot long slab. Some unfortunate sea creatures got stuck in here. You can see them. They represent something chemically and structurally different. You can also see a crack in here. It was filled in with some material, and again, it makes basically one big rock, even though it was cracked and filled in. And you can imagine that this material here might have different character, and it may be actually good to put a bunch of cracks in there, fill it in. It might end up with something that's kind of useful that way. Here's another one. I don't understand it. This was a cool example that was sitting there in the granite store. This again is about 10 feet long, going from end to end. And you can imagine that somehow some kind of process of forming rocks and nucleated in the middle moved out, and then these things impinged on each other and give you these regions like this, and there might be some kind of impurities swept out to regions like this that look different than color. This is all natural. It's really a cool example. This is the sort of thing that we live for in material science. And this thing happened over thousands of years probably. So as a result of it, these things are feet long, and when things go slowly, they tend to grow very large. Very big structures tend to happen with very slow cooling rates. We in material science like to have very fine structures typically, so we use fast cooling rates and end up with very fine structures typically. That's what we're after. But again, this is just another piece of granite. This one I kind of like because this one looks like a real metallic microstructure. Again, this is the long view of several feet. If we zoom in, look at a small region like this, we see these other regions where you've kind of got a white milky background here, and then other features that are more gray, and they kind of look similar. They're similar in size. And what I postulate is that this milky thing all is one sort of crystal. These other gray ones are a different sort of crystal. All the white is similar chemically and structurally, and all the gray is also similar structurally and chemically. This is shorthand for something I'll introduce formally in a little bit, of two different phases of material. The white is one, the gray is probably another. So what we're going to do is we're going to consider these things in terms of length scales and put some math onto this. If we start with a meter, the next smallest big thing we have in the SI units is the millimeter, and excuse the background noise, it's passing time, that'll be over soon. There's exactly a factor of 1,000 between millimeters and meters. 1,000 millimeters make up a meter. 1,000 microns make up a millimeter. 1,000 nanometers make up a micron, and that's the way we make materials. Another key thing that we might be interested in here is other units that are of use is the centimeter, which sits there, which is 10 millimeters. And an angstrom is close to an atomic spacing. Actually, about 2.5 angstroms make up one atom distance, typically. This, again, has a log scale. Everything in here represents multiples of 10, or between these major units, multiples of 1,000. So you can see if you're dealing always in microns, you can kind of deal in linear math. If you're going between one length scale here and here, you really have a hard time thinking linearly. You've got to think differently mathematically. I'm not going to go through this. This just shows kind of where there are different sorts of length scales associated with things we're interested in as humans. You know, human hand, crystal diameter, the particles I'll show you in a little bit in T6 aluminum, atom repeat distances, and again, this is all on a logarithmic scale with the big SI factors of 1,000 called out on there. These factors of 10 I mentioned before. There's some great ones. IBM did a great one back in 1977. Simpsons have done this as a couch gag. Morgan Freeman does a great job, and I will encourage you to just think about this on your own. Won't spend much time in lecture here. So anyway, here's microstructure. Here's a broad view. This is what we material scientists kind of live for. This is a typical thing we call a polycrystalline structure. It's maybe about 40 diameters. Crystals are highly ordered. They come together with grain boundaries. If you make really small crystals, they look something like this, where these are the ordered regions. There's sort of disordered regions between them. The sizes of these grains matter a lot. And then often we see crystals within crystals. This is an example I'll show you a little bit more of, where you might have one form of crystal here, and then get into the middle of this thing, we find that there's a different crystal here in the middle. And what we find is this is one form of order, and then there's a compound here that forms inside. Here's again another compound inside another crystal. And what happens is when you put these little crystals inside these big crystals, the defects that allow deformation to happen are called dislocations. You see these running through there. These particles make it very hard for the agents of deformation, called dislocations, to move through. It gives you very hard structures, and I'll talk about that a little bit more in a minute. So key bits of vocabulary I'd like you to get out of this are as follows. First of all, a grain is basically a crystal. Between crystals crystals is called a grain boundary. A phase are these areas that are distinct. Within a crystal, you might have secondary atoms kicking around that can be dissolved in there. Those are solutes. You can have various kinds of defects. You can have point defects, which are extra solutes, or maybe vacancies. You can have line defects, which are these dislocations. Planar defects, include the grain boundaries I tell you about, and then volume defects can be things like hole-out voids that exist in the material. And these can exist over this continuum of length scales. Again, atoms sit down around here, crystal sizes sit around here, and then you could imagine putting distances on these length dimensions on these kinds of defects. Typically, we're studying our line defects in around this region in the nanometers to microns. So this is one of the things that's really important and difficult in material science thinking, is keeping all your length scales straight. Okay, so let me show how this works and how length scales come together. So we've got our airplanes, which are really big things on the order of meters. They've got jet engines in them, again, that are on maybe 10 feet, 3 meters long. The heart of the jet engine is the hot zone. In the hot zone, we run nickel-based alloys, actually very close to their melting temperatures. The way we get them to maintain strength close to their melting temperatures is partly by making single crystals. That means there's sort of orderly alignment of all the atoms going about the same way across there. And then there's little crystals within the big crystals. So this is sort of a brick and mortar arrangement. And I'll show you again on the next slide. These bricks are made out of Ni3Al, a compound, and then the mortar is a solid solution of nickel plus aluminum that puts that together. If we zoom in, this is what this looks like. Again, this is the mortar structure, is this gamma, which is a nickel aluminum disordered alloy sitting there. And then there are these compounds that are very ordered, that they're in between them. That brick and mortar structure gives you these very good properties. This is what it looks like at a very fine scale. This is 300 nanometers here. So about 1 micron goes from about there to there. We have mu. And this is, again, 1 micron looking here. This is a zooming out. This is what you might see if you zoom out much, much, much further. You might actually be able to see the whole grain. This is what makes efficient jet air transportation possible, are these nickel-based superalloy microstructures. So in that, I've kind of developed the idea of phase that I want to develop a little bit more coherently. A phase is a region where the physical properties and chemical properties are essentially uniform and chemically distinct, and they're separable areas somehow. For example, you can have a jar like this of ice water. The ice cubes represent solid H2O. That represents one phase, and then liquid H2O represents the other. Chemically, it's the same thing, but they have distinct properties, being solid and liquid. That's a two-phase mixture. One that's technically a little more exciting is this is steel. This is what we call a fully perlitic rail steel. This is carbide, Fe3C, are these dark bits. That's one phase. And then the lighter phase that sits in here, like a region like that, is basically just iron. And if we cool this properly from austenite down into the austenite plus carbon region, we'll talk about that later, we can create these structures. This is pretty much what all rails look like. And shame on me, there's not a micron marker around there. That's probably about 10 microns in that in that case. So how do we look at these things? Optical metallography is the simplest thing we do. It's just like what we did with the countertops. We basically take something, cut the crystal, polish it, maybe put some acid on it. Then a structure appears on this. And in this structure, these are basically crystals. These linear defects are called twins within them. And that gives you the structure, and we can manipulate the grain size, the twin density, things like that, and make very interesting structures out of that. We can look at other things. This happens to be a cast structure, a very complicated one. These large regions are one phase. Each color represents a different crystal, meaning there's a different orientation associated with each. And then within this other region, you can see, you can zoom in, there's even more going on. This is a two-phase region. You can see two colors there. And you see an area around here where it's light near the large phase. This is a microstructure. Interpreting this is a key to material science. We're not going to get into this in too much depth here, but there's some great references, books shown above, websites with loads of microstructures on them, and if you want to get into that, we can do that in depth. But the important thing is there's what we call single crystals and polycrystals. Within a crystal themselves, atom up like this, and there's great order within them. Very seldom do we use single crystals in practice. There's two places that they're most common. One is in jet engine turbine blades I showed you a minute ago. Another one is in jewelry. Third one is in semiconductors. Most of the time, you've got small crystals that fit together like this and boundaries between them, or grains and grain boundaries, as materials people often say. And this is 30 microns here, and you see the grains. Each of these prominent axes are oriented differently in each of these grains. And what's important is that, let me get back to where I was. What's important is that there can be different properties along different directions. For example, if you take body-centered cubic iron, it has a much higher elastic stiffness along the body dimension, the body diagonal, because the atoms are more closely packed, than it does along this other direction, that what we call the cube direction. But they all fit together, and then they give you some average properties, and interesting things happen in between. That's, again, a much deeper story than we want to go into here. So again, these crystals can be compounds, or they can be single element based. On the left, you've got one of the prototype ionic crystals, sodium chloride. These are the sodium anions and the chloride cations that end up fitting together to form the structure. Again, these things can go on and on and on. And the thing is, you get this orderly packing where this direction is clearly different than that direction. You can see these all have the same type of atom. These, they alternate if you go that way. So another crystal structure is zinc sulfide, zinc blend structure. You see this is another fairly ionic crystal. And this is a crystal structure here for graphite, you see. And graphite is interesting in that you've got covalent bonding going in these sheets, and these sheets are held together with secondary bonding. So that gives graphite remarkable properties. Graphite, if you pull it in these sheet directions, you end up with very high stiffness, very high strength. That's why we make graphite composites for aircraft and things like that. And these secondary bonds that hold the sheets together, this is why we can use graphite for pencil lead also, because the secondary bonds just slough off. Again, there's lots of length scales involved here. Typically, again, your atoms are 1 or 2 nanometers apart. And then our grains might be on the size of about a micron to millimeters. So there's a big disparity between those things once again. Again, single and polycrystals, we can go further. Most of the time we take things and we roll them and we process them like you're taking something and taking dough with a rolling pin. That can cause your grains to elongate. It can also cause preferred crystallographic texture. And these are ways we can modify the material in quite powerful ways. Again, looking at these with simple optical micrographs is a great way to get an idea of what's going on. So the problem with light microscopy is light wavelengths are right here around 1 micron, is where what light wavelength is. That means you really can't see much smaller than about a micron. So you need other techniques to go back there. One of the great techniques we use is electron microscopy. Electrons also have some wave nature, some particle nature. So with the particle nature, you can do a great job of imaging. You can go down way below a micron. We can also do diffraction that I'll explain in a slide or so. We can also pull out chemical signatures. When you bombard something with electrons, it gives out X-rays. You can measure the energy of those X-rays, figure out what's in it. And we can't do justice in this course, but I will say here at Ohio State we're blessed with having some great microscopy facilities. This is what a scanning electron microscope looks like, an SEM. And there's a beam column here, sample goes down here, and then this is a detector that measures these X-ray wavelengths that come off, and it allows us to do chemical analysis. Some really cool things can be done. Diffraction is another technique. This ties into high school physics nicely. You've probably all seen Bragg's law, where we say n lambda is equal to 2d sine theta. You may or may not have seen that. What this is if you've got X-rays coming in, they've got a wavelength associated with them called lambda. They could be bounced off of crystals, and again, these crystals have characteristic spacings, and where those characteristic spacings d solve this equation for a given angle theta, you'll get constructive interference. You can measure those angles and find out the spacings that sit within the crystals. Other experiments you can do with X-rays, even X-rays that have a range of wavelengths, you can bombard those X-rays at a crystal along a line, and then send them out. You'll get a pattern, and that pattern reveals the crystal symmetry. You can see there's prominent directions going this way and that way for that crystal, and that has fourfold symmetry along that axis, and that allows you to do geeky things to figure out exactly what you've got there. Great technique. So for X-ray diffraction, we find crystal type, lattice parameter, crystal orientation, crystal perfection, symmetry operations, and so forth. We can do the same things with electrons. They will diffract also. The other thing we can do is image with these things. Again, 2 nanometers. We're down here. You can see these are the crystals. You've got atoms all lined up in slightly different directions. They come together at boundaries. There's defects along those boundaries. We can also look at impurities on those boundaries. And this gives us great insight as to how materials behave based on their structure. Also with transmission electron microscopy, we can look at the nucleation of very small new phases in materials. These are small second phases in precipitation in the aluminum, silver, copper system. And you can see these are about 50 nanometers across. That's on the order of about 200 atoms across going this way. These small precipitates play a big role in how dislocations, the defects that enable deformation, move through the crystal. They can really strengthen it. Understanding that is very important. Can't at all do justice to it here. The other thing that's interesting, you see crystalline directions indicated on this as well. Again, this 100 nanometers sits right there is where that is on that length scale. So again, much, much bigger than your atoms, which are sitting down there, and much smaller than what we can see as humans, which is up about there. Okay, the next thing I want to do is talk about cast versus wrought structures. And this is, again, good definitions you should know if you know a little bit about materials. Cast is simply that. You take something, heat it into the molten state, cool it. This is a cast structure. You see these tree-like features called dendrites here. These are crystals. In a case like a copper-nickel system, the nickel being higher melting point usually solidifies first, rejects copper out, so the area between these dendrites will be copper-rich. These areas within the trees tend to be nickel-rich. Those are interesting structures. They can be strong. Very often we do better if we can make the material homogeneous and make it equiaxed, make it small grains on it. So what we do is we heat that material up, roll it, then we can develop from this cast structure, we can develop a wrought structure. So this here is cast. Sorry. This down here is a wrought structure. And then we can take these wrought structures, for example, and run a weld bead through them. If we do that, we're basically reheating the material, so it's almost like putting a cast material. This is a cross-section you see here of a welded material into a wrought material. This solidified in place, develops another region where the material got heated quite a bit, changes the structure, and that gives us very interesting structures that, of course, are of much practical value also. So another example of this in use using the tools we have here at Ohio State is this is a program I worked with Mike Mills, Bob Hayes, King of Unisec on, looking at how superalloys crack. We can look at exactly what orientations grains are. We can also put other forms of defects into them by processing. And then we can figure out exactly which kinds of grains are cracking by using these tools, and then figure out what remedies we can put into the material to reduce cracking. So this is really important. It's how we keep power plants running longer. It's how we keep airplanes in the sky. And there's thousands of good engineers working on these kinds of problems every day. So I think I will close there. Just say microstructure is the heart of material science for all materials classes. We can change these microstructures by process, and then if we can control this microstructure, we can control materials properties, and that's the heart of what materials scientists do. So that's it. That's all. Please write me an email if you have any questions, and look forward to interacting with you all.